Hello to everyone, I'm Paulo Sorricchio, Master Student at DigiPen Institute of Technology, and with this video I'm going to show you Project 5 for the CS 541 course, Advanced Graphics. In this project we implemented View Frustum Culling. Basically, every time we draw something on the screen, as I was reading a Microsoft article on how to optimize graphics rendering code, and basically they said the fastest polygon you can draw is the one you're not drawing. And so this project is actually trying to make as few draw codes as possible, and how we're going to do that is basically we're going to go through some steps. View Frustum Culling is basically not drawing things that are not inside my frustum. The frustum is just when you define a camera is composed by 6 planes that are the top and bottom plane, the left and right planes, and the front and back planes. So basically everything that is going to be outside these 6 planes is not normally, if it's rendered, simply the graphics pipeline will compute the vertex processor for these polygons, and basically what happens for each primitive, and what happens is that the pixel processor is activated if and only if the pixel is actually on the screen after the projection transformation. So that means that we can save the vertex processor, and most important, we can save a driver code. That is really important. Nowadays on computers, the problem is that GPUs can really handle a lot of computations. GPUs nowadays are really powerful. The problem is that every time we are saying to the GPU do that, we're actually making a driver code. So every time the C++ code is executing code on the GPU, it actually has to go through the operating system, through a driver, and that is really expensive. Drawing a cube is more expensive, the actual driver code, than the just processing 24 vertices, and that's it. So this project is trying to avoid this cost, and basically what we're going to do is trying to do just simple cube intersection. At that point we're going to introduce two enhancements to this project. Basically we're going to have View Frustum Culling with bounding volumes, and the bounding volumes are going to be a hierarchical axis-aligned bounding volume. So we're going to build a tree of bounding volumes around our scene, because for example, let's suppose that we have this scene here. Let's suppose that all this scene is outside my view frustum, like now. It wouldn't really make any sense checking all the boxes. Let's suppose we have one big box around all the scene. If the scene is all outside the screen, we just have to check one. And what we do for the check is we basically transform the 6 planes equations in word space, and we check for each box. And yeah, so basically this is the first step we can do. The tree enhancement that we're gonna use to make this code more efficient is plane coherency and masking. So there are the two implementations. To do that, we have a special mode, and with the special mode you can actually see that the informations here are going to be activated, and there we go. So now masking and plane coherency are not activated. As we can see, we have the object outside the frustum, now 0 because all the scene is inside. The object inside the frustum, all the 11 by 11 grid, and the plane evaluations 12 because basically we have to check with each plane if they're inside or not. So and the objects intersecting the frustum. So as we move the scene, we will start to see the object intersecting the frustum number. That's it. Like the right cube here now is touching the right border, and we see object intersecting the frustum 1. So as we move, we see these numbers changing, and so you might be saying, wait, why are you doing just 12 planes evaluations here, and here the planes evaluations go crazy? Well, that's because when I'm here, as I said, I just have to check if the main bounding box around all the scene is inside or not for each of the 6 planes. What I have to do when the let's say the scene is half through the frustum. basically we have to check, oh, the big bounding volume is not intersecting, but wait, maybe this small bounding volume is not intersecting, so we can discard this one. Oh, but the right one is intersecting, so we have to go down the tree and try to understand where is the bounding volumes that is intersecting with the Frustum, and try as usual to make as few draw calls as possible. So if we activate masking, we're gonna see that the planes evaluations are gonna still be 12, but the numbers, while I'm gonna move the scene inside or outside the Frustum, are gonna be really low with respect to before. Let's see, 150. Let's see the highest, 200 with respect to 1,107 planes evaluation. It's like less than 1/5. It's really a good optimization. We were just doing really as few plane evaluations as possible, because of course, I mean, evaluating planes, it's not free. We're because there's always this trade-off. If of course a driver call is expensive, but at the same time, if we to not make a driver call, we have to use 4 cores and try to understand if that triangle is not inside. Sometimes it's just better to just draw the thing and not worrying about whether the object is going to be inside or outside the Frustum. So I mean, this, for example, in this example, is not really worth it because all these polygons are just cubes. We could use some kind of instancing to do this. So in one draw call, we basically draw all the boxes, and so that would definitely increase performance. So with just one draw call, we're drawing all the boxes. Even with different parameters, it's instancing is a technique to do that. But this is just to demonstrate the view Frustum Culling, basically. So in this case, as I said, masking now is active, and as we see, the plane evaluations number is definitely lower than before. What happens if we activate plane coherency? With plane coherency, now it's activated, as you can see. Let's see what happens when the whole scene goes out of the screen. There is just one plane evaluations. Even if I move this, now I'm moving my mouse, that means I'm moving. You see, when I move my mouse, the scene is moving even when it's outside the screen. There's just one plane evaluation. What happens if I deactivate plane coherency? If I deactivate plane coherency, it says 3 planes evaluation. This kind of funny, because basically you have to find an order for doing plane evaluations, and basically what I'm doing is bottom, left, right, top, front, back. So you can see from the number, so it's 3 planes evaluations, because basically when I move all the scene outside, it has to check, hey, is it intersecting with this one? No. Oh, maybe with this one? No. Oh, it's outside of here. So yeah, if it's outside here, it's gonna be always outside the other planes. I mean, if the whole scene is farther than the most right edge, it's never, I don't have to check with the other planes. And then you can see the order of the planes, because basically if you can move this down, it's 5. Oh, so it's not it's an error. It's not the order is not that. Oh, the order is left, right, bottom, top, back, front. So as you can see here, yes, it's here just one plane evaluation, because basically this is the first plane I'm checking. This is 3 planes evaluations, because basically this is the second plane I'm checking. 5, 7, then let's go into the scene. As we can see 7 here again, and we should see 11 in the front plane. Let's see, plane evaluations 12, 11. Here it is. So yeah, that's basically the Frustum Culling project. So let's activate both, and we see that yeah, the numbers are definitely, the optimization is definitely worth the work of dividing the tree. Moreover, I have a way to show you how the tree is composed, and as you can see, pressing the H button, you can see the hierarchy. So this is the first bounding volume. As I said, this is the main bounding volume. It's the one outside the whole scene, surrounding the whole scene. And I put a way to go down the tree and to go back to see all the bounding volumes of the tree. So we're basically navigating the tree with V and C. So if we press V, we see that the 2 bounding volumes now are this one. This is all pre-processing, but it's done almost instantaneously. So when you start the program, it calculates all the bounding volumes, and it does in less than a second. It's really fast. And so yeah, if we go down the tree, we see the hierarchy of bounding volumes. We start to see that they're dividing, that the algorithm is dividing this is always the scene. Remember, this is the scene. Is dividing the scene is always smaller boxes, and we're gonna start seeing. Okay, here for example, you see these cubes here. These are bounding volumes for a single model, single cube, for example here. So the next level, they're going to disappear, because basically that is you cannot divide, you cannot make a bounding volume that is smaller than the object itself. That is the object, so that is the smallest bounding volume you can do. So we're gonna see boxes disappearing the next level. As I said here, disappearing. We always see smaller bounding volumes, and yeah, this is our hierarchy. So this is the last level of our hierarchy, and yeah, that's pretty much it. As usual, you can download this project and try it on your computer. You can go and visit my website at www.palosricchio.com. I'm gonna put a link at the end of this video, and yeah, that's pretty much it. I hope you guys enjoyed this video, and well, see you guys next time.